Alvikan Bharti with your mentor Avilas Sarkar. Now we will move on to more number of observation regarding the matrix. The next comes observation. It says number 2 that if two matrix is multiplied and it is equal to the another two matrix where one matrix is common, if I get the value of these two, but in algebra what we can say that if m into n is equal to m into p, so then if m is non-zero, the same thing that as matrix is non-zero, then we can say n is equal to p, but where we cannot definitely say this is equal to 0, sorry, we cannot say this is not 0, not definitely can say, okay, that A into B, if the matrix is equal to A into C, we cannot say B is equal to C. We cannot, we cannot predict or say that B matrix is equal to C matrix. So we'll take an example. A specific example is there. If I take the A is 1 0 1 0, B is 0 0 1 1, and your C is 0 0 2 3. So now the rule is I have to do AB. So AB, if I multiply, what I will get 1 into 0 0, 0 into 1 0, that means 0, 1 into 0 0, 0 into 0 here, 1 into 0 here, 0 into 1 0 here again, 1 into 0 and 0 into 1 is equal to 0. So I am getting AB is equal to all 0. So there is a 0 matrix. Okay. So let me write it like that, 0 matrix, I need not to write. So A into C is equal to what? A into C, that means 1 into 0 0, 0 into 2 here is equal to 0, this equal to 0, 0 into 0, that is equal to 0, 1 into 0 here, and 0 into this is equal to again 1 into 0 0, this one, this second also 0. So you can get AB is equal to AC. Matrix is all both 0, but here is, if you see the matrix individually, B and C are not equal. Okay. So this is a similar, this is a different kind of pattern is coming, where if the common matrix number of all the one column having 0 and the reverse other matrix with which I am multiplying is keeping one row 0, then that case this is possible. So this will follow a pattern. If we see matrix which is common to, which is multiplied to both the matrices, having one complete column having 0 elements, and the things that with which I am multiplying having one complete row, here is column, here is row, because this is coming first. So we know the column of the first has to be same as the row of the second. In that aspect, if you want to bring some idea within you, so that we will say that whatever the matrix coming first, one column of complete, if it is carrying 0 and with which I am multiplying, the one row is completely 0, then the product has to be always same. It will get the same product. Okay, but individually the matrices with which the common matrix is multiplied are not same. So this is one rule. Okay. The next one is number 3. If AB is 0, as I seen in the earlier case, in algebra what we can see, m into n, if it is equal to 0, then the value of n either be 0 or n is equal to 0, or m and n both equal to 0. This we can conclude. But here we cannot conclude that A is equal to 0 or B is equal to 0 or either is equal to 0. We cannot conclude that. Okay. So the same example I will move here. I will take A is equal to, as I seen the complete row in the earlier example, this the same thing you can carry. You can carry any. So here one complete column of this which is placed first with the matrix which is placed second, as the all complete row, one complete row has to be 0. In this case, what you will find, AB must be equal to all 0. Definitely will get all 0, but individually if we say these are not. Next rule is it is just comparative to the algebraic rule. As in algebra we say that if a plus b whole square is equal to a square plus 2ab, or minus we can take plus minus 2ab plus b square, but in matrix that does not follow, or else a minus a plus b or a into b, if I do, I will get a square minus b square. That also does not follow in matrix, so you cannot say this. Okay, so for that, if I take an example to prove it, you can prove it, but it will be very lengthy process. So okay, so let me check with any common matrix where I will take A B B A. Okay, and the matrix B is equal to, I am taking C D, or sorry, what we can take B A A B, just reversing this. Okay, so let's try this. When A plus B, if I calculate, we calculate matrix. Okay, so if I calculate, so addition is possible of two matrix. Well, this is A plus B will be there, and there A plus B will be there again. A plus B, yes, this A plus B will be there, A plus B also there. So in all this case I can take A plus B common, and this will become 1 1 1 1 matrix. Okay, so now if I square it up, so that means I am multiplying A plus B into A plus B. So what is that mean? A plus B also a matrix. If I multiply it with A plus B, okay, so I am multiplying this two matrix. So this is A plus B whole square will come outside, and this will 1 1 1 1 matrices will be multiplied 1 1 1 1. So this is equal to A plus B whole square into 1 into 1 plus 1 into 1 2. This will be 2 2 2. So this 2 also can come out, A plus B whole square, and this will become 1 1 1 1, ultimately of this form. Just remember this. Now if I calculate individually all that part, A square, that means A into A. So A is this one, A into A. If I calculate this, AB BA, so this is my final result. This is become, what is that? I'll write it 2AB in initial place whole square 1 1 1 1 I found. Okay, so this I will multiply AB BA. So this will be equal to if I multiply it, what will we get? A square B into plus B square I will get here, AB and AB, then 2AB, then this is equal to 2AB here, and this is equal to B square plus A square I will find. Okay, this will be the case of A square. So and B square will be, if I do calculate B square, that means BA AB, if I calculate with BA AB, so that will give you what b square plus a square, b square plus a square, ab 2ab will come here, b square a square plus b square I will get 2ab I will get. So this will be the case, and if I calculate ab, sorry, a into b, this is in the same order, so this is equal to what, a into b, b into a, 2ab, a into plus a square plus b square, b square plus a square, 2ab, then again. So if I add all this, a square plus b square plus 2ab, what I find, I will expand this, so this will be a square plus b square whole square, and then minus 4ab whole 4a square b square. And again it will be the same, no, this will be the different one, ab, so that will be this minus this will be 0 then, and this is equal to b square, and ab is equal to this into this is equal to again this minus is equal to 4 a square b square, and this minus a square plus b square whole square, that will be 2 into that, so 2 will be multiplied, so this will be 8, 2ab, that means 2 will be multiplied, this will be 2, so ultimately this will become 4a square b square minus a minus square plus b square whole square. So if I take common, this will be minus a square minus b square whole square, 4ab is a minus, so this will be the ultimate answer. But here if I calculate, this will be, this matrix value is 0, so this will be 0, there I am getting a definite value. So you can see a plus b whole square not equal to a plus a square plus 2ab, that is not, because what I am getting a plus b whole square value is become, for this matrix it will be 0, whereas the right hand side I am getting minus a square minus b square whole square. So these values are not equal, because a not equal to b, I cannot say a is equal to b, you cannot say is not equal to b, so this is definitely not equal to 0. So you can understand by this example. So similar you can try with this and you can find this rule true. Okay, so you cannot follow the algebraic rule in matrices. Okay, so this is the ultimate understanding or conclusion, you can say. The next one is related to this next one was this is 5, you can say. If A, B, C are of matrix of same order and A, B are two scalars, so what I am saying, A, there are three matrices of same order, okay, and the elements A and B, small a, small b, are two scalars, then what is that? That A plus B will equal to B plus A, and this is equal to B plus A. So that means if I do the summation, so the first rule is summation is commutative. Summation is commutative. Commutative means when you change the position of matrix. When A is at first position, B is in second. If I do the reverse, so automatically you can understand if a matrix is of A, B, B, A, another matrix of B, A, A, B. If I take the simplest one, So if I do addition, so the elements are being added. So even if you change the position, the value won't change, isn't it? If we see, if we keep this first, so b plus a, only thing is a plus b will become b plus a, but the value of this will same, because elements is a individual numerical. So that numerical follows the algebraic rule. So when it is following the algebraic rule, so reversing it will not change the value, but it is not changing its position itself. So changing the position of the matrix, it will change the orientation of each element, whether it will come first and second, that will not change the value of the numerical. So this will follow. Okay, so that means summation individually is a commutative. The second one is associative. This is called associative. Three matrices are there when this brackets is following the Bodmer's rule, where this bracket will come first for calculation. If I do a plus b first, then we'll add c. This won't change if I do the other way around. If I do a plus b plus c, or let's say a plus c plus b, if I do for this, then that is associative. Means that can be associated with any of the matrix to start with, but the result won't change. Okay, so that means it is the summation is associative to associative. Okay, so summation is commutative, associative. Now the summation, there is no distributive rule is coming, because distribution comes when there is a multiplication comes. So that possible of the rule with the summation is commutative and associative. That means commutative means when place will change, associative means it can associate to any other to start with. Okay, and other thing, if a matrix with summed with any zero matrix, it won't change its value. This is following the algebraic rule also. Okay, and if matrix is added with negative of this matrix, negative of the matrix, it becomes zero. That also true. Okay, because this negative is being associated as a scalar of -1 with the matrix. This will be multiplied to all the elements. So this will give you a zero result. So other was, if I say these are scalars a and b, so two scalars added with the matrix, this could give you the same result if we do add, if we do multiply the scalars first then add, or add the scalars then add then multiply with this matrix, because this is all are scalars, this is only numerical values. So if we add these scalars then multiply with the matrix, it will give you the same result. If you do individual multiplication of the scalars of the matrix, then add the matrices, because this will turn into some other matrix, let's say a1 then 2. Now if we add this, you will get the same matrix which we will find here as, let's say, a3. So this will give you same matrix. Okay, so the value will be same. What next here? So other rule is, if the multiplication rule also follow with the scalars, it won't change if I multiply with b. Okay, this way. Okay, ab, or if we do ab into a matrix, this also okay. So if you do consecutive multiplication with matrix A, or reverse the scalars and multiply, or multiply the scalars and multiply then with the matrix, will give you the same result. Okay, and this also I know the identity matrix with A, will give you the matrix itself that I have proved already. And if you multiply 0 with the matrix, so this will become a 0 matrix. Okay, so these are the small rules that anyhow it is possible to understand. I need not to give you a real example, whereas you can try yourself at home. And there I will end my this episode. And next episode I will bring few more rules that need some explanation, because when it comes as a multiplication, the rules are a bit different from the summation and subtraction. Summation and subtraction follow the same rule. If it is also with the first two rules with the addition, same is applicable with the with the subtraction. But only thing is that subtraction is not commutative. So that means if I say a minus b, it cannot be equal to b minus a. This is not commutative. So subtraction is not commutative, whereas it cannot be commutative as well associative. Means if I say a minus b minus c, it cannot be like that. In this case it's okay. If I say this can be done, or this can be done, but if I say a minus of b plus c, if I say like this, so there this could be somehow this also possible. Yes. So subtraction, there is no rule given in any of the textbook, but from your common sense you can understand. If I do a minus b, then after if I subtract b, because it is a consecutive subtraction of the elements, so if I do calculate all this negative sign together and subtract, that will give you the same result. Now let's say if I take an example, let's say 5 6 and 3 2, and if I take any example of b is equal to 1 2 2 1 and c is 3 1 1 3. Now we do try this so that you can understand. First thing, we try the commutative law of a minus b with this 2. So a minus b is equal to 5 minus 1 is equal to 4, 6 minus 2 is equal to 4, 3 minus 2 is equal to 1, 2 minus 1 is equal to 1. Okay, now if try b minus a, this will give you the reverse one. This is minus 4. Okay, this is minus 4, this will definitely minus 4, this will give you minus 1 and minus 1. So this means this is minus of what? This matrix, that means minus of a minus b. So you will get the negative of the matrix as a result. So this could not be same as this. So this is not commutative. So subtraction is not commutative. Let me check associative or not. So we'll do a minus b first, then we'll subtract c. So a minus b, anyhow what I am getting, 4 4 1 1. Then I will subtract c, that means this 3 1 1 3. So if you subtract, so what will get? This will give you 1, this will give you 3, this will give you 0, this will give you minus 2. So remember this. Now we'll do a minus of b minus c, b plus c, because this minus being added. So this I am getting 1, this one. So a minus b plus c, this I will add 3 plus 1 4, this is 3, this is 3, and this is 4. Okay, now what I get, a is equal to this 5. So ultimately 5 minus 4 is equal to 1, 6 minus 3 is equal to 3, 3 minus 3 is equal to 0, 4 minus 2 is equal to 2. So you see, this will be minus, no, 5 minus 4 is equal to 1, 6 minus 3 is equal to 3, 3 minus 3 is equal to 0, 2 minus 4 is equal to minus 2. So now see this value. So you can say the subtraction is associative. This can be done like that, okay, but I am not changing the order itself, okay. So this is associative. So for addition it is commutative as well as associative. For subtraction it is not commutative but associative, that we can prove. So here I will end this session. In the next session I will bring some more properties that will be related to multiplication, okay. So thank you for now.